Hello students, welcome to the class. Today we will start the new chapter, Classification of Elements and Periodicity in Properties, Theory Part 1, which is NCERT Chapter 3. Disclaimer, the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. So, for the preparation of this chapter, you should first look upon the NCERT. Then, for the case of exception, you can look for the understanding in J.D. Lee and O.P. Tandon. After that, try to practice as much as question possible for different competitive exams. Coming on to the basic topics of this chapter. First of all, we will see the periodic trains, including the atomic, ionization, electron affinity, electronegativity. Then our focus would be on the exceptions. The third point would be revising the important concepts, which includes highlighting the periodic law. We'll see it in the coming slides. Then trying to classify the whole periodic table into S, P, D, F block, and also important property related to them, which is diagonal relationship. Then there are some common mistakes which children often do. So when we'll study about the electron affinity. You will see exception there regarding the fluorine and chlorine. And I will tell you the difference between the electron gain enthalpy and electronegativity. So these are two far different things. So do not confuse between them. Then relating to the diagonal relationship, we will see the anomalous behavior of the second period elements. And lastly, as I said, solve as much as PYQ is possible, and also attempt the mock test, which is there in our Sathee website. For the case of learning of this trends and all, try to use mnemonics, okay, short tricks for learning the periodic table, for learning the different trends. Our today's class objective would be learning about the concept of grouping elements. So why do we need to group it? So that is important to learn, and that also in accordance to their properties. Now this grouping led to the development of periodic table. According to the NCERT, we will cover the topic why do we need to classify elements, which is section 2.1. And second, we will learn about genesis of periodic classification, NCERT section 2.2. So the very first point which should come to your mind, that why we need to classify elements. We know that if I talk about any matter that you see around you, including this table, any chair or water molecule, they all are made up of elements. Now, if I talk about 1800, then out of these elements, only 31 elements were known. Then by 1865, just after 65 years, this counting goes to double. Now, 63 elements are identified till 1865. But if I talk about the present situation, there are 118 elements which are known. And the good part is that, and I would say the miracle part is that some of the elements are discovered by man. And this process is still going on regarding the synthesis of new elements. But the point here is that why do we need to classify elements? See, we have now 118 elements, and each of these elements have unique property. If we learn them individually, so that would be very difficult to contain, and the data is also very vast. So, with such a large number of elements, we need to classify in such groups on such periods so that their properties would be same regarding the physical and the chemical. And in this attempt, scientists search a scientific and a systematic way to do this. So what did they do? They studied about the chemical facts, okay, and try to group those elements which have the same chemical properties in one period. Now, in that process, various number of scientists were involved. We will talk about them one by one. So the first one is the Daubernier law of triads. Now, Daubernier, what he did, he take three elements. Okay, he took three elements and made such groups in innumerable ways. Okay, and he named that group of three elements as triads. In doing so, he has seen that the middle element of that triad has the atomic weight equals to the average atomic mass of the elements that are present on the either side of the middle element. And second thing that he observed was that these three elements which is present in one triad, they all have the same property. So this can be understood with the help of a table. So this is your first triad, which has lithium, sodium, and potassium. Lithium has an atomic weight of 7. Potassium has an atomic weight of 39. Now, if you take the average of the atomic weight of lithium and potassium, you will find that their average atomic weight is equals to the atomic weight of sodium, which is 23. This is the first thing. So just add 39 plus 7, divide by 2, you will get it as 23. So this is the first triad. And the second thing that they observe is that these three have similar properties. These three elements have similar properties. Moving on to the next triad, which involves calcium, strontium, and barium. Then again, do the same thing. Add the atomic weight of the calcium and the barium. Remember, you have to add the atomic weight that is present on the either side, not the middle one, like your strontium here. And the same goes for the chlorine, bromine, and iodine. Now you can try and calculate the average by yourself. You will get the atomic weight equals to the middle element in each of this. Like the first triad, you will get the weight of sodium. Second, you will get of strontium, and the third one, you will get it of barium. Now, let us move to the second attempt made by the Newlands. So, the English chemist John Alexander Newlands in 1865, he founded the law of octaves. In this process, what he did, he took the elements and arranged them in the order of increasing atomic weight. But he observed that after every eighth element, the element has the property, means the eighth element has the property of the first one. So we'll look to this on a table. Then he compared this chemistry thing with the analogy of your notes, the musical notes. There are 8 notes, you know. So the relationship was developed in this way. So he named it as law of octaves. But the problem with this Newland law of octave is that it is only true up to calcium. After calcium, this was not followed. And although this idea was not accepted at that time, but he was given the Davy Medal by the Royal Society of London in 1887. Now, this is your Newland's octave table. So first is the lithium, then beryllium, boron, carbon, nitrogen, oxygen, and fluorine. This includes 7 elements. Now, rather than going on to the 8th element, we are putting that 8th element below the lithium, because the property of sodium resembles the property of the lithium. Again, move on further. Sodium, potassium, aluminum, silicon, phosphorus, sulfur, chlorine. As we come on to the 7th element, then again come back to the first one, potassium. So we are placing the 8th element below the first element in each row. But the difficulty is that after he did up to calcium, the next element has no property similar to that of aluminium. Okay. So due to this reason, his classification was not very helpful in dividing all the elements known at that time. I guess this thing is clear to all of you. Then the last is the Lothar-Mayer's arrangement of periodic table. What he did, Lothar-Meyer, so he took the same atomic weight and he plotted a graph. Graph between what? Between physical properties. That can include your atomic volume, melting point, or boiling point. Okay? He plotted a graph between the atomic weight and the atomic volume. The second graph would be between atomic weight and melting point, and the third graph between atomic weight and melting point, boiling point. Yes, the lithium, sodium, and potassium will have the properties in common. No, the problem is that the lithium was not the first element. Basically, he started from the lithium. So at that time, the aim was not to put all the elements in a shell. They were taking a bunch of elements in such a way so that their classification can be done in a good way. But later on, we see the long form of periodic table. There he took all the elements. Now, this is the graph that he plotted. See, start from the lithium, which is at the left side, then beryllium, then carbon. You can see that after carbon, there is a rise in the graph at the sodium point. Then again, it goes down, sodium, magnesium, and aluminum. Next, it again started to rise, silicon, then phosphorus, sulfur, chlorine, and again potassium. So these elements that are at the peak, they were put in one line. Okay, so lithium, sodium, potassium, rubidium, and cesium. And you can see the same in the new long form of periodic table. Similarly, the corresponding beryllium and magnesium can be seen in the same group. Okay, so this was the plot that was used by Lothar-Meyer to understand the periodicity. So again, I am repeating it. There was a plot done between the physical properties and the atomic weight. So the first is between the atomic volume and the atomic mass. So this graph is for the atomic volume and the atomic mass only. He also plotted it for the melting point and the atomic weight, for the boiling point and the atomic weight. And for all of these three, he got the same graph almost. Then came the Mendeleev periodic law. So this was the most advanced theory after before the long form of periodic table. We know that in 1868, Lothar-Meyer did that same thing. So he also followed the Lothar-Meyer's trend by using the atomic weight. Remember, students, till now, each and every classification that we have seen is based upon the atomic weight. And Mendeleev also used the same thing. But the point is that Mendeleev was given a much better credit both for the modern periodic table as well as the periodic law. We will see his periodic law and also the periodic table that he put forth for explaining all of the elements. So what was his periodic law? So this is the most important point of the Mendeleev periodic table. He said that the properties of elements are a periodic function of their atomic weight. Means you can think of atomic weight as the justifying factor for the property. If we arrange the given element in terms of the atomic weight, we will get the properties of elements classified. So now some important point related to the arrangement of elements by Mendeleev. So Mendeleev arranged the element in the horizontal row and the vertical columns of a table. And he did that in terms of increasing atomic weight. But the important point that he mentioned is that he did not follow that increasing atomic weight trend strictly. Instead, he relied upon the properties. If he sees that two elements have the same property, then regardless of what atomic weight they do have, they put them in the same period and the same group. Okay. And that is the reason the Mendeleev system of classifying element was more elaborate than that of the Lothar-Meyer's, because he took the property as a more classifying factor for the given elements rather than the atomic weight. Yes, two things are there to emphasize here. First, what Mendeleev did, he arranged the given elements in increasing order of their atomic weight. But if he sees that your increasing atomic weight is not justifying the position of the element, then he put the element in that position where its properties are significant to the previous one. So we will try to understand the same with the help of a table. So as I said, the second thing which he took care of, so what was the basis of that? I said that he emphasized on the chemical properties. So what was the basis of that? So the basis of that was the empirical formula and the chemical properties. So first of all, the most important point is empirical formula. He made the element react with different elements and saw that different elements were forming different oxides. Suppose one is forming AO2, the second is forming B2O. Then he will not keep those two elements in that same period. But if he sees there is a C element and that has the same type of oxide that the A have, that has CO2, suppose there is AO2 and CO2. So he will place the A element and the C element in the same row because they have the same chemical properties. And in doing so, he saw that most of the, means some of the, I would not say most of the, some of the elements were facing difficulty in their placement as their atomic weight were not strictly followed. But what he did, he ignored the atomic weight. He said that, okay, there may be a case that the atomic weight would have been weighed incorrectly. And keeping the atomic weight aside, he just took the properties similar, the elements whose properties are similar, and kept them in one place. If I take the example of it, suppose your iodine, which is having a lower atomic weight than that of tellurium, which is present in group 6. Now, iodine has a lower atomic weight and tellurium has a higher one, and he placed it in the group 7. But we know that if tellurium has a greater atomic weight, it should come after the iodine. Okay, but it was not the case. He put the iodine first and then the tellurium. Sorry, he put the tellurium first and then the iodine, and tellurium was having a greater atomic weight. Why did he do so? Because if we keep iodine after tellurium, then and then only we will get your iodine below the other halogen elements, which are fluorine, chlorine, bromine, and all. Okay. So again, I am repeating it. So this is just an example that how Mendeleev focused upon the properties and not on the atomic weight. So he saw that your iodine is having a smaller weight than tellurium, but he put the iodine after tellurium because to keep the iodine in that same line where the fluorine, chlorine, and bromine, which are the halogens, so these are the halogens, could be kept in the same line. I hope this is clear to all of you. So all these elements which have -1 as the valency, I would say -1 as the adds the valency, are called as the halogens, like your fluorine, chlorine, bromine, and iodine. Now next, this was the most miracle point of the Mendeleev. So what he did, he left some gap inside the table, in his table. For what? For those elements that were not discovered. Okay. He said that there will be a discovery of an element that will fit that gap. This is the first thing. Second thing he said was he would be able to predict the chemical and physical properties of that undiscovered element based on the other elements that are present in that same line. For example, the gallium and germanium were not known at that time when the Mendeleev periodic table was published. Now what he did, he left gap for them down the silicon and down the aluminium. He left two gaps for the undiscovered elements, the gallium and germanium, and he named them as Ika aluminium. So he said that, okay, there will be an element which will be discovered in future, and he named them as Ika aluminium and Ika silicon, and also predicted the properties of both the elements without doing any experiments on them based on the elements that were already present in that line. So this was the greatest discovery of his table. Now let us look at his table, which he prepared for explaining the properties of aluminium, Ika aluminium, and Ika silicon, which later came to be known as the gallium and germanium. See how accurately he measured those properties. He predicted that the atomic weight of the Ika aluminium would be 68. And when gallium was found, this atomic weight was found to be 70. It is so close. And not only that, if you look at the germanium's predicted atomic weight, it is 72, which is too much precise to the actual germanium atomic weight. Okay. Now let us see the density. You can see that for the unpredicted, I would say the predicted Ika aluminium has a density of 5.9, and the known gallium has a density of 5.94. So this is one thing. Then you can look for the oxides and chlorides formula also. This was the empirical formula that I was talking about. He know that the elements that are present above this Ika aluminium has a oxide formula as A2O3. So A can be any element. In this case, it is your gallium. So he said that the element that would be discovered at that time, it would have a formula of A2O3. And at the present time, it is known that the gallium has a formula of Ga2O3. Okay, now you can take both atomic weight and atomic mass. There is no distinction in case of chemistry for both the terms. Now coming on to the chloride. The same thing was seen for the chloride, that the gallium has a formula of GaCl3 and he predicted it as GeCl3. Okay, predicted it as ECl3. Similarly, for the germanium, he said that there will be a valency of 4. Okay, and it can be seen in the GeCl4 formula. So this was the table he put forth for explaining his all of the periodic trends. Now, if you look for the silicon and your a gap that is left below the silicon, you can see that how beautifully he arranged those. Okay, he arranged those and he placed some gaps here. So there are some dashes there. You can see it very clearly below the iodine, below the tellurium, below the antimony. Okay, similarly below the xenon, below the gold. So those dashes are representing the vacant gaps for those elements which are not discovered, which were not discovered at that time. If you look at the third group, okay, at the third group, the first one is boron, then the scandium, and then the gallium. Okay, so here I have placed the gallium and the germanium, but at that time, a gap was left for these two. Again, I am repeating it. So there is no difference between the atomic weight and atomic number. There was almost the same discussion, right? So means the same value would be there for the atomic weight and the atomic mass. So Mosley was the one who ended this debate of the periodic law. We'll talk about that in another class. But before that, we should try to appreciate the Mendeleev's periodic table by focusing on its significance. So, according to him, he was able to do a systematic study of the elements. Okay, he simplified and systemized the study of the elements, and he placed those elements which have the same properties in the same groups. Now, if you know the property of the first element that is present in that group, you can predict the properties of the upcoming elements, okay, without doing experiments on it. Now, there would be exceptions, but at least you would be able to predict a large amount of its properties without doing experiments on it or without calculating them. Now, what was the second significance? It was the prediction of new elements. As we have seen just now, that there were some gaps left in the Mendeleev periodic table. And although only 63 elements were known at that time, he left gap for almost all of the elements that are discovered today. Okay, so we have seen it that Mendeleev left some blanks and spaces and gaps for that unknown elements. And these gaps were for the gallium, germanium, and other undiscovered elements. Then what is the third significance? The third significance was that he said that I am not able to arrange this given elements in the order of the atomic weight because their atomic weight would have been calculated incorrectly, or they are just a calculational mistake. And this prediction helped in correcting the doubtful atomic weights of many elements. For example, beryllium was assigned an atomic weight of 13.5 at that time when he was systemizing the elements, but you know it very well that this is not the true value. Okay, and due to this, he also got, at that time, they also got the wrong valency. But we know it in our present time that beryllium has an atomic weight of 14 and not 13.5. As a result, it should be placed between carbon and nitrogen. Okay. So if he was taking, if you had been taken the 13.5 as the correct, I would say the correct atomic weight, then he would have placed the beryllium at a different place. But since beryllium was not fitting in that position due to its different physical and chemical properties, he placed the beryllium between the carbon and nitrogen. And this further came to be true. Similarly, there were no vacant spaces for the in between carbon and nitrogen because your beryllium has an atomic weight of 14 and not 13.5. If it was 13.5, then it would have been placed between the carbon and nitrogen. No, the modern periodic table is not based upon the Mendeleev's periodic table, but yes, it provided a very great framework for it. You would see it that the framework of the Mendeleev's table and your long form of periodic table are quite same. As a result of this, beryllium was assigned a valency of 2 and was placed as a position between the lithium and boron. Okay. So the basic defects in the Mendeleev periodic table was, first of all, the position of hydrogen. So hydrogen has properties both of the group 1A, which is your what? Which is your alkali earth metal, and the group 7A, which is your halogen. So as a result of that, hydrogen couldn't be placed anywhere. And the position that was given was not justifying its position because its properties were not similar to either of this group wholly. So this position was controversial. Second thing is the pair of elements. We know that some elements with higher atomic weight precede the element with the lower atomic weight. So although with today's precision, if you try to arrange them in the increasing order of their atomic weight, then you would get a wrong form of the periodic table because the atomic weight was not the periodic function as stated by the Mendeleev. It was your atomic number. We'll see it. Suppose if we take the example of argon, its atomic weight is 39.9 and of potassium it is 39.1. If you look at the periodic table, you will see that argon comes before potassium. Okay? Because their atomic number is the main deciding factor, not your atomic weight. If you take the atomic weight, then you will put argon after potassium. Similarly, you can take the example of cobalt. So cobalt has an atomic weight of 58.9, whereas nickel has an atomic weight of 58.7. But still, cobalt is placed first and then the tellurium is placed. So it is not in the true order of atomic weight. And lastly, your tellurium, it comes before your iodine. And Mendeleev did not give any justification for this ambiguity. So this is the second defect. The third one is the position of isotopes. We know that what are isotopes? These are those elements which have the same atomic weight, different atomic weight, but same atomic number. So here is an example for you. Chlorine has an atomic number of 17 So both the chlorines are having the same number, but their atomic weights are different. One has 35, the second one has 37. Yes, the atomic number is the important one. We will look at the modern periodic law, which is in accordance with this atomic number thing. So, according to the Mendeleev classification, this should have been placed in two different places. So, listen it very carefully. They have a different atomic number. Both the isotopes have different atomic number, different atomic weight. If they have a different atomic weight, then they should have different positions, because Mendeleev said that you should arrange the elements in the increasing order of the atomic weight. But it is not so, because they both have the same chemical properties. Okay, we have learned about it in the atomic structure chapter, where we have seen that isotopes have the same chemical properties. So, there was a problem with this atomic weight. Similarly, you can take the example of hydrogen. It has three isotopes: protium, deuterium, and tritium. They have different atomic weights, 1, 2, and 3. But still, in the Mendeleev's periodic table, these three elements have no specific, I would say, no unique position in the table. And we can see it in the long form of periodic table that they have the same position for all the isotopes, whether it is protium, deuterium, and tritium. They are all represented by the same symbol, and same case is applicable for the chlorine. Now, the next one, there were some dissimilar elements which were grouped together. Okay. For example, the alkali metal such as lithium, sodium, and potassium. So in this table, which is the group 1A, group 1A, which includes the lithium, potassium, and the sodium, that contains copper and Ag and Au. But their properties are completely different. Okay. And at the same time, certain chemically similar elements like the copper and the Hg, they have been placed in different groups. So two things are there. First of all, the copper and the mercury, they have the same property, but they are placed in different groups. So it is written as 1b and 2b. But the elements such as your lithium, sodium, and potassium, and the group copper, silver, and gold, they are placed in the same groups, like 1A and 1B. So this was the difficulty with the Mendeleev periodic table. And last difficulty was the position of element in the group 8. So noble gas did not have any proper positioning in the modern periodic table. Okay. And as a result of that, you could see in the Mendeleev table that they have a group 0 assigned to them. Now, due to all this defects in the Mendeleev periodic table, it was later removed, and we are now dealing with the modern long form of periodic table. So this was all from the theory part. Now we will see the DPP related to it. So just wait for a while I open the DPP.